Imagine standing on solid ground, feeling the quiet certainty that beneath your feet lies something stable, unmoving, eternal. For centuries, humanity has believed that the earth beneath us is a predictable system. Layers of rock, slowly shifting tectonic plates, molten currents deep within the mantle, each part governed by well-understood physical laws. From earthquakes to volcanic eruptions, we have learned to interpret the signals of our planet, translating them into patterns, models, and forecasts. But something changed. In the past few decades, scientists began detecting anomalies, subtle, almost imperceptible disturbances, deep below the Earth's surface. At first, they were dismissed as measurement errors. Instruments can fail. Data can be noisy. And when you're studying processes thousands of kilometers beneath the crust, uncertainty is expected. But the anomalies didn't go away. They appeared in seismic readings taken from entirely different parts of the world. Sensitive detectors designed to measure the propagation of earthquake waves began to record something unusual. Waves that should have behaved in predictable ways were bending, accelerating, or even slowing down in regions where no known geological structure could explain it. The deeper researchers looked, the stranger it became. To understand what they were seeing, we need to journey into the Earth itself. Beneath the thin crust lies the mantle, a vast region of semi-solid rock extending nearly 2,900 kilometers downward. Beneath that, the outer core, liquid iron and nickel, swirling in turbulent motion. And at the center, the inner core, a solid sphere of metal under unimaginable pressure. For decades, this layered model has served as the foundation of geophysics. Seismic waves, generated by earthquakes, travel through these layers, changing speed and direction depending on the material they pass through. By studying these waves, scientists can map the invisible interior of our planet. It is, in essence, a kind of planetary ultrasound. But then came the unexpected. In certain regions deep within the mantle, seismic waves behaved as though they were encountering something else. Not solid rock. Not liquid metal. Something that didn't fit into any known category of Earth material. At first, these regions were small, localized anomalies that could be explained away as unusual mineral formations or temperature variations. But over time, as more data was collected, a pattern began to emerge. These anomalies were not random. They appeared to form vast, interconnected zones stretching across thousands of kilometers. Some were located beneath major tectonic boundaries. Others lay hidden beneath stable continental interiors, far from any known geological activity. And they were doing something no one expected. They were exerting influence. Seismic waves passing through these zones weren't just distorted, they were being guided, redirected, as if an unseen force was shaping their paths. Scientists began to ask a difficult question. What if these anomalies weren't just passive structures, but active phenomena? What if something beneath the Earth was interacting with energy in ways we didn't yet understand? The idea was controversial. After all, the laws governing the Earth's interior are rooted in physics we know well. Heat transfer, pressure dynamics, material science. Nothing in these frameworks suggested the existence of an unknown force. And yet, the data continued to point in that direction. Then came another clue. Gravitational measurements, taken by satellites orbiting the Earth, began to reveal tiny but consistent irregularities in the planet's gravitational field. These were not the large-scale variations caused by mountains or ocean trenches. These were subtle distortions, shifting over time, as though something deep below was redistributing mass in ways that defied conventional models. At the same time, geomagnetic observations added another layer to the mystery. The Earth's magnetic field, generated by the movement of molten metal in the outer core, is known to fluctuate. But in certain regions, these fluctuations appeared to correlate with the same areas where seismic anomalies had been detected. It was as if three separate systems, seismic, gravitational, and magnetic, were all being influenced by a single, hidden factor. Scientists began to connect the dots. Could there be a process deep within the Earth that we have never observed before? A mechanism capable of altering wave propagation, shifting mass distribution, and interacting with the planet's magnetic field? Or something even more profound? Imagine a force, not unlike gravity or electromagnetism, that operates under extreme conditions. A force that only becomes significant under the immense pressures and temperatures found deep within planetary interiors. It sounds like science fiction. But the history of science is filled with moments where the impossible became reality. Forces once invisible became measurable. Phenomena once dismissed became fundamental. So researchers began to look closer. They deployed more sensitive instruments, expanded global seismic networks, launched new satellites capable of detecting minute changes in Earth's gravitational and magnetic fields. And as the data poured in, a new picture began to take shape. The anomalies were not only real, they were dynamic. They shifted over time, slowly but measurably. Regions of influence expanded and contracted. Wave patterns changed. Gravitational distortions drifted. Whatever was causing this, it wasn't static. It was evolving. And then, something even more surprising emerged. Deep beneath certain regions, particularly under parts of the Pacific Ocean and Africa, scientists identified enormous structures within the mantle. These structures, known as large low shear velocity provinces, or LLSVPs, were already known to exist. They are vast, continent-sized regions where seismic waves travel more slowly than expected. But now, these structures appeared to be linked to the anomalies. The boundaries of these provinces seemed to coincide with areas of unusual activity. It was as though they were either generating or channeling the unknown influence. And that raised an even deeper question. What if these structures weren't just geological formations, but something more complex? What if they were interacting with a force we have yet to understand? The implications were staggering, because if a previously unknown force exists within the Earth, it could change everything we think we know about planetary science. It could reshape our understanding of how planets form, how they evolve, and even how they sustain magnetic fields. But perhaps most unsettling of all, it might mean that the Earth is not as stable as we once believed. That beneath our feet, hidden far below the surface, something is moving, shifting, and influencing the very fabric of our planet in ways we are only just beginning to perceive. And as scientists pushed deeper into this mystery, they began to uncover evidence that would challenge not just geology, but physics itself. Because what they discovered next was even more surprising. As global datasets grew more precise, scientists began to notice that the anomalies were not only influencing seismic waves, they were altering time itself, albeit in the smallest measurable ways. Atomic clocks, the most precise timekeeping devices ever created, had been placed in orbit and across the Earth's surface to study gravitational time dilation. According to Einstein's theory of relativity, time moves slightly slower in stronger gravitational fields. This effect is well understood and routinely accounted for in satellite systems like GPS. But in certain regions, the measurements didn't align perfectly with predictions. The differences were tiny, fractions of a nanosecond, but consistent. Time appeared to pass at slightly different rates over areas that corresponded to the same deep Earth anomalies identified through seismic and gravitational studies. At first, the discrepancies were dismissed. Measurement uncertainty, environmental interference, calibration drift, these were all plausible explanations. But as the data accumulated, the pattern became impossible to ignore. Something beneath the Earth was subtly altering the flow of time at the surface. The deeper researchers looked, the more interconnected the mystery became. To explain these observations, scientists turned to extreme physics, conditions that push the boundaries of known theory. Deep within the Earth, pressures exceed millions of times those at the surface, and temperatures rival those on the surface of the Sun. Under such conditions, matter behaves in unusual ways. Exotic phases of minerals can form. Atomic structures can rearrange into configurations never seen in laboratories. Electrons may flow differently, and magnetic properties can shift dramatically. But none of these effects, individually or combined, could fully explain the anomalies. So researchers began exploring more radical possibilities. One idea emerged from the field of condensed matter physics, the concept of emergent forces. In certain complex systems, collective behavior can give rise to new phenomena that are not apparent from the properties of individual components. For example, temperature is not a property of a single particle, it emerges from the motion of many. Similarly, superconductivity arises when electrons move in coordinated ways under specific conditions. Could something similar be happening within the Earth? Could the immense pressure and heat be creating conditions where a new, emergent force arises, one that only exists at planetary scales? It was a bold hypothesis, but it offered a framework that could unify the observations. A force that interacts with energy and matter, influencing seismic waves, altering mass distribution, and even affecting time through subtle changes in spacetime curvature. To test this idea, scientists turned to simulations. Using some of the most powerful supercomputers in the world, they modeled the behavior of materials under extreme conditions, incorporating quantum effects, thermodynamics, and large-scale dynamics. These simulations revealed something intriguing. Under certain conditions, clusters of atoms could enter synchronized states, forming structures that behaved almost like coherent fields rather than random assemblies of particles. In these states, energy could propagate in unusual ways, more efficiently, more directionally, and with properties that resembled known forces, but didn't fully match any of them. It was as though the material itself was becoming something new. Meanwhile, experimental physicists attempted to recreate similar conditions in laboratories. Using diamond anvil cells, devices capable of generating immense pressures, they compressed materials to extremes, observing their behavior under controlled conditions. Some experiments hinted at unexpected transitions. Materials exhibited sudden changes in conductivity, magnetism, and wave propagation. While none of these experiments directly confirmed the existence of a new force, they suggested that matter under extreme conditions could behave in ways we are only beginning to understand. Back on Earth's surface, observational data continued to evolve. Seismic tomography, essentially 3D imaging of the planet's interior, revealed that the anomalous regions were not uniform. They contained internal structures, gradients, and boundaries, almost like ecosystems within the mantle. And these ecosystems appeared to be interacting with the surrounding material. Heat flow patterns shifted near their edges. Plumes of hot material, rising from deep within the mantle, often originated at their boundaries. These plumes are responsible for volcanic hotspots, such as those that formed the Hawaiian Islands. But here's the surprising part. The timing and location of some volcanic events seemed to correlate with changes in the anomalies. It was as if something deep below was influencing processes at the surface, guiding where and when energy would be released. Scientists began to realize that this unknown influence might not be confined to the deep Earth. It could be part of a larger system, one that connects the core, mantle, crust, and even the atmosphere in ways we don't yet fully understand. And then, a new line of evidence emerged from an unexpected source: neutrinos. These nearly massless particles are produced in vast quantities by nuclear reactions, including those occurring within the Earth's core. Because neutrinos interact very weakly with matter, they can pass through the entire planet almost unaffected. But detectors designed to study neutrinos began to observe slight variations in their behavior when passing through certain regions of the Earth. Again, the differences were subtle, but consistent. Neutrino flux appeared to change depending on the path taken through the planet, suggesting that something within the Earth was influencing even these ghostly particles. This was unprecedented. If confirmed, it would imply that the unknown phenomenon was not limited to conventional matter and energy interactions, but extended into the realm of particle physics. The mystery was no longer just geological. It had become universal. As researchers from different disciplines, geophysics, quantum physics, astrophysics, came together, a new picture began to form. The Earth was not just a static system of layers and processes. It was dynamic, interconnected, and perhaps governed by principles we have yet to fully uncover. And at the heart of it all was this unknown force, or emergent phenomenon, quietly shaping the behavior of our planet from within. But even as the evidence mounted, a crucial question remained unanswered. What is the origin of this force? Is it something that emerged naturally as the Earth formed and evolved over billions of years? Or could it be something even older, something embedded in the fundamental structure of matter itself, only revealed under the extreme conditions found deep within planets? The implications stretched far beyond Earth. If such a force exists here, it could exist in other planetary bodies. It might influence the behavior of gas giants, the formation of stars, or even the dynamics of galaxies. And that possibility led scientists to one final, profound realization. Because what they were uncovering beneath the Earth might not just change how we understand our planet, it might change how we understand the universe itself. It might change how we understand the universe itself. Imagine, for a moment, that the Earth is not unique. That deep within other planets, beneath the crushing atmospheres of gas giants, within the metallic cores of distant worlds, or even inside rogue planets drifting through interstellar space, similar conditions exist. Pressures beyond comprehension. Temperatures that reshape matter at the atomic level. If the unknown force beneath Earth is real, then it may not be confined to our planet alone. It could be a universal phenomenon, one that only reveals itself under the most extreme environments nature can create. Scientists began to revisit data from other worlds. Observations of planets like Jupiter revealed unexpected patterns in gravitational and magnetic fields. Subtle inconsistencies that had long been attributed to measurement limitations or incomplete models. But now, viewed through a new lens, these anomalies took on a different significance. What if they were signs of the same underlying phenomenon? The deeper researchers looked into planetary science, the more connections began to emerge. Magnetic fields, for example, are thought to arise from the movement of conductive materials within planetary interiors, a process known as the dynamo effect. But not all magnetic fields behave as expected. Some are stronger, more chaotic, or more stable than current models predict. Could an unknown force be influencing these systems? Similarly, heat flow within planets, how energy moves from the core to the surface, has always been a complex puzzle. Traditional models rely on convection currents and thermal gradients. But these models sometimes fail to explain localized variations or sudden shifts in activity. Again, the possibility emerged that something deeper was at work. Back on Earth, the implications became increasingly tangible. If this hidden force influences seismic behavior, it could reshape how we understand earthquakes. Regions once thought stable might, under certain conditions, become susceptible to unexpected stress accumulations. Conversely, areas known for frequent activity might be partially stabilized by interactions we have yet to fully comprehend. Volcanology, too, could be transformed. The movement of magma, the timing of eruptions, the formation of new land, these processes might not be governed solely by heat and pressure, but by deeper interactions occurring far below the mantle. And then there is the question of energy. If this phenomenon involves the emergence of new forms of interaction within matter, it raises the possibility, however distant, of harnessing similar effects. Not in the literal sense of tapping into the Earth's core, but in understanding the principles that govern such behavior. History has shown that fundamental discoveries often lead to unexpected technologies. Electricity, once a curiosity, became the foundation of modern civilization. Nuclear physics, once theoretical, unlocked both immense power and profound ethical dilemmas. Could this unknown force represent a similar turning point? For now, such ideas remain speculative. The phenomenon is still not fully understood, and much of the evidence is indirect. But the trajectory of research suggests that we are only at the beginning of a much larger journey. One of the most intriguing aspects of this mystery is its subtlety. Unlike earthquakes or volcanic eruptions, this force does not announce itself dramatically. It operates quietly, deep below the surface, influencing systems over vast timescales. Its effects are measurable, but only with the most sensitive instruments and the most careful analysis. It is, in a sense, a hidden layer of reality. And perhaps that is what makes it so profound. Because it reminds us that even on a planet we believe we understand, there are still forces at work that remain beyond our current knowledge. It challenges the assumption that science has uncovered all the fundamental interactions governing the natural world. And it invites a deeper question. What else have we yet to discover? As research continues, New missions are being planned. More advanced satellites, more sensitive detectors, more powerful simulations. International collaborations are forming, bringing together expertise from across disciplines to tackle one of the most complex puzzles in modern science. Each new piece of data brings us closer to an answer. But it also opens new questions. Because the more we learn about this hidden force, the more it seems to blur the boundaries between established fields. Geology merges with quantum physics. Planetary science intersects with cosmology. The Earth becomes not just a subject of study, but a laboratory for understanding the universe itself. And perhaps, in time, we will come to see our planet in a completely new way. Not as a static sphere of rock and metal, but as a dynamic, evolving system shaped by forces both known and unknown. A world where the deepest mysteries lie not in distant galaxies, but beneath our very feet. Imagine that. The ground you stand on, the landscapes you see, the mountains, oceans, and continents, all influenced, in ways we are only beginning to perceive, by something hidden far below. A force that has been there all along, waiting to be discovered. And as we continue to explore this mystery, one thing becomes increasingly clear. The story of Earth is far from complete. In fact, it may only just be beginning. Because what they discovered next was even more surprising. As global datasets became more refined, scientists began to notice something that went far beyond seismic distortions or gravitational irregularities. The anomalies were not isolated to physical movement alone. They appeared to be influencing fundamental measurements of reality itself. Across a network of ultra-precise atomic clocks positioned both on Earth and in orbit, researchers detected minute inconsistencies. These clocks, accurate to within billionths of a second, are designed to account for even the slightest relativistic effects predicted by modern physics.